Okay, let's start. So in the last class, we looked at how to improve the resolution of flash ADC by interpolation. So we started off with basic interpolation in voltage domain, and then we saw how the same can be done efficiently in the time domain. And the premise was based on the fact that the decision on the information on whether a particular input voltage is greater than or less than the middle reference voltage, that is additional reference voltage you want, also lies in the time taken by the comparators to make the decision. So you saw if the input is lying here, the top comparator will take longer time than the bottom one. So by detecting which of the two comparators is making decision earlier, we can get an extra bit of information for free, and that we could do using an SR latch. And we also saw how we can extend it for 4x interpolation also. So yeah, so let's say we take a flash ADC, say it's a 4-bit flash. Say the final binary output you get is say 1011 or something, and then you do this 2x interpolation. Let us say the decision from that is say 0. Now we have to stitch all these guys together to form a 5-bit data, right? So how will you put it? You will put the 0 here or here. Understand the question, right? You already have 4 bits from the flash. You have made an extra bit of, you got an extra bit decision from this time interpolation.
In the middle of the things, because we used to so
think about it, I'll not explain. So yeah, I mean there are two options. I mean, okay, maybe according to Manan there are 3 options. Then you can either put here at the LSB side or at the MSB side, or maybe you can put somewhere in between. So think of where it will. Cool. So let's continue today. So let us say you have taken the course till this point, you know how to design flash ADC. So let's say you get motivated, start a company, design a flash ADC, and let's say you sell it. And let's say you have chosen some particular process and you have designed the fastest flash ADC possible in that process. Say that speed is 0.5 gigahertz. So if this is the speed, what is the clock period? Yeah, what is the inverse of it? That's what I'm asking. 2 nanoseconds. Okay, now this is all working fine. So you have sold this, and then let us say some other client comes and says, hey, I also need an ADC, same resolution, but I want my ADC to be able to sample at 1 gigahertz. That translates to 1 nanoseconds of sampling time. Right? So what would you do? Would you choose a different process and design it from scratch? Or can you do something with the existing process itself? In the existing process, this is the fastest you can get, let us say. So is there something you can do on top of this?
do ADC, and then keep it in a like half time period. First this will do, then this will do, then this will do.
Yeah, okay. So is everyone getting that idea? I mean, let's say this is your signal, right? So right now the sampling period of my ADC is 2 nanoseconds. So which means it is taking the samples at, let us say 0, 2 nanoseconds. Let's say this is 0. This is 2 nanoseconds. 6. Now what I want is the final data to be available, to be sampled at 1 nanoseconds essentially, right? So in addition to this, I also need samples at, let us say 1 nanoseconds, 3 nanoseconds, 5 nanoseconds, and so on. You can easily get these blue samples from the first ADC here. In addition to this, I need these samples in green. The spacing between these samples, what is that? That is also 2 nanoseconds. So to get this, what can I do? I can use another ADC which can get these green samples. So I'll have an identical ADC, give the same input, but what is the difference?
The clock.
The sampling edge, the sampling instant for the second ADC is delayed. That's all, right? So this is, let us say the clock given is phi of t. So this is sampling at 0, 2 nanoseconds, 4 nanoseconds, and so on. What should be the clock given to this? Phi of t minus 1 nanoseconds. I mean, remember, if you give 5 bar of t, it will just flip. You just want this to be
Not
delayed.
that bar. I thought not any arbitrary bar where we get.
Understood? Yeah. Basically, if you delay this clock by 1 nanoseconds, so now because it's delayed by 1 nanoseconds, it will take samples at 1, 3, and 5, and so on. Fine. So in this way, if you have two ADCs operating at the rate fs by 2, by using these two in parallel and by skewing the time instant for one of the ADCs, you can actually get an effective sampling rate of fs. And this principle is called time-interleaving. And in particular, this is 2-channel or 2x time-interleaving for obvious reasons. And in practice, to design any high-speed ADC, this is the principle that is adopted. And again, I don't have to stop here with 2x interleaving, I can go for a nx interleaving. So let us say I have an ADC sampling at fs by n. I want to realize an ADC at fs. What do? I need to have n ADCs. So let's say this is the second one. And if this is a clock to this is phi of t, what is the clock given to the second one? Remember, this is sampling at fs by n. So what will be the time instance at which this guy will sample? No, I mean it's sampling at fs by n. What is the time instance at which it will sample?
N by fs, 0.
I mean, yeah, basically 0, nts, 2 nts, and so on. Now, what should be the delay to this clock? Finally, I want data at 0, ts, 2 ts, and so on, right?
Yeah. 0, n minus 1 ts. No, it should not be 0.
I mean, I should, let's say I want to, this is giving 0th sample. I want to get the sample at ts. What should I do? Yeah, I should delay it by?
ts.
ts. If I delay it by ts, this will sample at ts, n plus 1 ts, and so on. For the third channel, it should be delayed by 2 ts. For the nth channel, no, not nts. Nts is so this will give the. So of course now I get all these n output. So at the output, how do I stitch them to form a single data bit? I mean, I have this n outputs. Finally, what do I do to get a single data? How do I combine? I mean, what should I do? This is the data I'm getting from each channel, right? I basically have to multiplex, right? First, I should choose the data from this guy. The second sample must come from this guy. Third sample must come from the second channel, and so on. So you basically have to put a multiplexer that operates at fs. So it will basically switch between each channel one by one, and then it will keep repeating it cyclically. Is that okay? Fine. So this is often called NX time-interleaved ADC. Time-interleaved. In short, TI-ADC. Okay. Great. And okay, what I mean, in which application do you think? In which application do you think demands ADC with the maximum speed?
Sensors.
Sensors are really slow, right? I mean, sensors meaning it is sensing some physical quantity, and all physical quantities change very slowly, right? Temperature, pressure doesn't change so fast. To put it in other words, what is the fastest speed or fastest data rate that you have heard as an end user? Yeah, what is the fastest speed that you have heard? Nothing beyond that? Any data transfer, what is the maximum speed that you have heard of? Okay, I mean, okay, to put it in different. So let us say I want to transfer, I mean, at least this must be clear that we will need high speed ADCs in some data transfer application, right? So do you think we can transfer data at a faster rate through wireless communication or through wired communication? Huh? Yeah, but that's what the data transfer can be done at a faster rate through a wired medium or through a wireless medium.
Wireless means
Why? See, wireless medium, you are basically getting information from thin air, right? You are transmitting data to space and you are capturing it back. There is going to be a lot of loss in the wireless medium, right? So you cannot do it at a much faster rate. But wired, it's simple, right? You have something here, you have the receiver here, just connected, right? And this is where you can get really high speed data transfers. And what are some examples for wired? Huh? Optical fiber. And what do you use in day-to-day life? Right? You have USB,
yeah.
you have here this one,
This wire rather than
everything.
Bluetooth,
Yeah, and even this LAN gigabit Ethernet. And this is where this application is where demands maximum speeds. And I mean the speed can be as high as hundreds of gigabits per second, right? And in these places, again, you can't get ADC sampling at those 100 gigabits per second using a single channel. You have to interleave multiple of them and use it. So remember that next time whenever you connect to internet through LAN cable or data transfer through USB, a bunch of this time-interleaved ADCs are operating in the background. Okay. So now this looks like a nice principle. So let us say I have a 1 megahertz ADC. I put 1000 of them in parallel. I can get an effective sampling rate of 1 giga samples per second. I can put 10,000 of them in parallel and get 10 gigahertz. So in principle there seems to be no limit, right? So what do you think will limit this in practice?
the clock that we provide.
Hmm?
Precision in the clock of the delay.
Okay. Yeah. One thing is that so what he's saying is this is exactly TS delayed, but in principle, I mean in practice you cannot achieve this exact time shift. That is definitely one thing. And in general, basically any kind of mismatches in each of these channels will screw us up. Here the entire premise is under the assumption that we have n identical ADCs being used in parallel. Okay. But in practice, by the time there are no two things which are exactly identical, there will be some mismatch between any two things, and any kind of mismatch will affect us. And that is why in practice we'll see that this we don't do this a lot, because as you keep increasing the number of these channels, as we'll see now, the non-idealities we'll have will be much stronger. We can't correct for it. So let's see what are the possible mismatches we can have. I'll take a 2x interleaved ADC. So let's say this is the first ADC. This is the second ADC. Each of them is operating at fs by 2. So this is ideally should get a clock of phi of t. This should get phi of t minus. What should be the clock given to this? TS. So what are the possible mismatches? I mean, one thing he told is this. So this time shift need not be exactly TS. Let's say there is some delta t. Yeah. What are the other kinds of mismatches we can think here? Which one? That's what that we have captured. In addition to this, what other mismatches do you foresee here? Mismatches between the two ADCs. So what can happen is we'll see that, right? At least we'll try to see what are the mismatches that is possible, and we'll see if that is indeed a problem. If it is a problem, we'll try to correct for it. That's all. So one straight thing can happen is ideally the ADC should directly sample the input with a gain of 1. Let us say there is a small gain error. So let us say, and this is different for the two channels. Now in addition to this, any ADC will have some offset. Whatever you do, there is going to be some offset, and this offset can be completely different for the two channels. So these are the three possible mismatches we can have. So we'll try to see what is the effect of each of them and see how we can correct for it. So let's start with offset. So again, I'll start with a simple two-channel ADC. We'll understand what's happening, and then we'll extend the result for an NX interleaved ADC. So right now we'll assume that there is only mismatches in the offset. So let us say this is x of t. So ideally the samples here must have been x of 0, x of 2ts, x of 4ts and so on, right? And here it should have been x of ts, x of 3ts. Now what will be the signal I'll have, samples I'll have? Because of the offset, what will be the change I'll have? Here all the samples will be offset by constant VOS1. Here I have VOS2. So which means when I multiplex the data finally, what is the final x of n I'll get? First sample will be taken from the first channel. So it's going to be x of 0 plus VOS1. The second sample is from the second channel. That's x of ts plus VOS2. And third will be x of 2ts plus VOS1 and so on, right? So to analyze this, the simple thing is to try to express the sample we get in terms of the ideal data that we expect. The ideal data we expect is just x of 0, x of ts, 2ts, 3ts and so on. So if I were to represent this guy in terms of the ideal sequence, how can I represent? I mean, the ideal data is just x of 0, x of ts, x of 2ts and so on. The actual data we get is x of 0 plus VOS1, x of ts plus VOS2 and so on. So what is the simplest way in which I can model this? So let's say something you are going to. Yeah, I mean what? So basically, I'll have VOS1. Fine, that's all. Basically, in addition to the ideal data, we are adding some error sequence, and that error sequence is alternating between VOS1 and VOS2, right? So of course, this is fine. This is what you want. We'll see what happens because of this guy. So the error sequence we have is basically alternating between VOS1 and VOS2. So if I look at the spectrum of this sequence, how will it look like? Okay, let's say is this a periodic sequence or a non-periodic sequence? What is the periodicity of this? It's a discrete time sequence. Discrete time sequence, two samples. So what is the fundamental frequency? Discrete time 2 pi by 2, which is pi. So we have a periodic signal in discrete time with the fundamental frequency of omega naught. If you have any periodic sequence, if I look at the spectrum, what are the sinusoidal frequencies I'll observe? If you have any periodic signal with some fundamental frequency, and if I look at its spectrum, what are the frequency components I'll observe? I'll only get the harmonics of this. This is what Fourier made you study few semesters before. Basically, I'll have k times omega naught, right? So any periodic sequence is going to only contain its harmonics. That's all. So for k equal to 0, it's simply DC. For k equal to 1, it is pi. For k equal to 2 pi is same as 0, right? So essentially in discrete time, we have only two distinct frequencies. Okay. So if I map it to continuous time, so 0 is basically 0. What does pi translate to? Our sampling rate is fs. Fs by 2, right? So if I look at the spectrum of the final data I get, I'll get the ideal data sequence, spectrum of the ideal input. In addition to this, I'll observe two tones. one at DC and one at Fs by 2, right? So we'll basically have something like this. Let's say this is the data. So we'll get an additional tone here. Yeah, I mean that's okay. This is a discrete time spectrum. I'm just writing the frequency axis in Fs. If you had to write the spectrum in discrete time, it's going to be minus pi to plus pi. That's all. Now this is for a 2x. By the way, this is good or bad? What we get here? Is this okay or not okay? The input signal we gave was this, but if there is mismatches in the offset, we get this as the output spectrum. So I'm asking, is it fine or not fine? Not fine. Simply because you will incorrectly infer that your input itself had these tones, right? And please notice that the issue here is not because we have offsets in the ADC. The issue is because the offsets in the two ADCs are different. If this indeed the two offsets were indeed exactly equal, this will just be an additional DC offset, and that is usually okay. Okay. Now this is the case for a two-channel interleaving. If I have an n-channel interleaving, what will be the error sequence I'll have? So I'll have offsets from each of them, BOSN, and then it will repeat, right? So what is the periodicity of the sequence? N samples. What is the fundamental frequency? 2 pi by n. If I look at the spectrum, I'll see only the harmonics of this. And if I map it to continuous time frequency, what are the frequencies? 2 pi maps to what frequency? 2 pi maps to Fs. So this is k times Fs by n. Right?
It keeps on increasing and this whole.
Yeah, that's what. So if k takes what values? 0 to n minus 1, right?
Yeah.
Because after n it's simply 0. So if I look at the spectrum now, as you see, I'll have a whole bunch of tones here, 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 and so on. Right? So as you see, if you keep increasing the number of channels, the number of these spurious tones will also keep increasing, and it's going to be really chaotic. So we have to do something to actually correct for this. So, and please note that the problem arises here because the offsets in each channel is different. That's all, right? So can you suggest something to correct for this? Let me draw an n-channel interleaving. So we have some offset here in each channel. The first channel, I have some offset. This is the nth channel. VOS1, VOS2. Yeah. So can you suggest me something to correct for this mismatch in the offsets? What can be done? Till this point, whenever we had offset in the circuit, what was our approach to correct for the offset?
We used to minus that offset.
We somehow get an estimate of that offset and add some quantity in the reverse polarity, right? Now, where do you think we can add this offset in the reverse polarity here?
After ADC.
Yeah. Basically, in principle, you can add here and here, but adding things in the digital domain is much easier, right? So what you can do is, in principle, go and add things here, a small digital number which corresponds to this. Is that okay? And note that we don't actually want offsets in each channel to be exactly 0. We want only the offsets in each channel to be same. So what you can do is, we can assume that the first channel is okay. We'll take this as a reference channel and then try to match offsets in all the other channels to this offset. So I should basically add, what should I add here then?
VOS1 minus VOS2.
So I'll add VOS1 minus VOS2. So here I'll add this. And this is usually referred to as digital calibration. This will be a recurring theme in this course also. And in any analog and mixed signal circuit, you will find that any kind of mismatches or offset is usually tackled by this digital calibration, simply because you can do a lot of post processing in the digital domain easily than in the analog domain. And in mixed signal circuits, you have information already available in the digital domain, so you just try to exploit. Now, of course, the next question is, how do I know what is the number to add here? Again, there are multiple ways in which you can do. So one thing is, let us say we apply a sinusoid. Ideally, if there is no offset, if I take the average at the output, what will it be? Should be 0, but with offset, there is going to be this VOS1 here. So what you can do is, you take the average of each guy. So this is going to give me VOS1. So you do the same thing here also. I want to keep the average in each of these channels to be equal to this, right? So you go and compare. For each channel, you go and compare it, and then have some kind of an optimizer, and then go and change this guy. Okay, so I don't know, you might have heard. Are you guys familiar with any kind of optimization? Mean squared, least mean squares. You can put least squares, least mean square, anything here. That goes and corrects for these weights. And the objective function is to try to minimize the error between the average in the first channel and the average in the other channel. And this you can easily do in the digital domain. So this is with the offset. So now let's look at what happens if there is mismatch in the gains. So again, I'll start with a 2-channel case and then extend it. So now there is mismatches in the gain. So now tell me, what will be the samples I'll get here? I'll have k1 x of 0. Here it will be k1 x of 2ts and so on. Here I'll have k2 x of ts, k2 x of 3ts and so on. Right? So if I stitch the final data, I'll get k1 x of 0, k2 x of ts and so on. So again, the idea is same. We'll try to represent this in terms of the ideal samples I should have gotten. So how can I model this in terms of the ideal data?
Multiply by that.
Yeah, multiply by?
K1, K2.
Yeah, I'll basically k1, k2. Is that okay? So in the difference is, in the offset case, the error signal was getting added. So here a similar error sequence, which is also periodic, is getting multiplied. That's all. So let me copy this. So now let us say the input is a sinusoid at a frequency, say Fn. What will be the frequency content of the sequence? It is a periodic sequence with 2 samples. We have only 2 frequencies, and what are they?
0 and pi.
0 and pi in continuous time frequency.
0 and fs by 2.
Fine. So in time domain, we are multiplying these 2. So what will happen to the effective thing? What will be the frequencies in this product sequence? You have a sinusoid at Fn, we are multiplying with a sinusoid at DC. What will be you'll get Fn. So here you have a sinusoid at Fn, sinusoid at Fs by 2. Multiply the 2 sinusoids. What are the 2 frequencies I'll get? Yeah, I'll get basically sum and product. So it will be Fs by 2 plus or minus Fn. And if I look at a spectrum in single sided from 0 to Fs by 2, what are the frequencies I'll consider? No, I'm saying I'll get these 3, right?
Yeah.
And I mean, basically, if I only look at single-sided spectrum from 0 to fs by 2, what are the frequencies that will be present? So, please remember that fs by 2 plus fn will indeed alias back to fs by 2 minus fn. Both are same. So, if I look at the spectrum now, if this is 0, I'll get a tone at fn. That is what you expect. You get it. And let us say this is fs by 2. I'll also get an spurious tone at this frequency. So, what is the spacing of this? That is also fn. Fine. So, because of this is also called the image frequency. And by the way, so in this sequence, we know that we have only a DC term and a tone at fs by 2. What is the strength of the DC term? Basically, I'm asking what is the DC in this sequence or the average of the sequence. What is it? This is the sequence, right? K1 plus K2 by 2. So, which means the tone I'll get here strength will be proportional to K1 plus K2 by 2. Right? Because this one you get when Fn convolves with the DC. So, similarly, can you tell me what will be the strength of this Fs by 2 tone? It cannot be K2, right? I mean, okay, see, when we are doing this, I know the sequence is this, right? K1, K2, K1, K2. This is the periodic sequence. When I am doing this Fourier decomposition, I am saying that this sequence can be thought of as sum of sinusoids. How many sinusoids I have here? Only two sinusoids. One is DC, that is K1 plus K2 by 2. That's always same, right? DC. So I should add only one other sequence. So what should be the sample that should come here so that the addition of this is this? K1 minus K2 by 2. What should be the term that should come here so that addition gives this? Huh? K2 minus K1 by 2, I'll write as minus, and the next term will be K1 minus K2 by 2. And remember that, I mean, a sequence of alternating 1 and minus 1 is a tone at fs by 2. That is, if you have a signal at fs by 2, sample at fs, you will basically be sampling these points. Right, because this is the sampling period. Sorry, this is the sampling period. You will be sampling alternating 1 and minus 1. And I mean, you can also know, right? I mean, fs by 2 in discrete time maps to a frequency. What is the discrete time frequency for fs by 2? Pi. So sinusoid at pi, e power j pi n, what is it? It's minus 1 power n, right? So whenever you have an alternating signs, right? 1 minus 1, 1 minus 1, that is indeed a tone at pi, or you can think of it as a sinusoid at fs by 2 being sampled at fs. Okay. So yeah, the strength of fs by 2 tone is proportional to k1 minus k2 by 2. So which means the image strength is proportional to k1 minus k2 by 2. Right? So does it make sense that the strength is proportional to k1 minus k2? Why? Why does it make sense that the additional image frequency we get, the strength of that image is proportional to k1 minus k2? Right? You know that if there is no mismatches in the gain, if k1 is equal to k2, we don't get this. Right? So that is why this is proportional to k1 minus k2 by 2. So again, this is for a 2 channel. Let's quickly see what will be it for n channels. Let me erase all this. So again, if I do it for an n channel, what will be the error sequence? I'll have k1, k2, k3, kn, and then it will repeat. So we'll have a periodic sequence with n samples. What are the frequency components I'll have? What is the fundamental frequency first? What is the fundamental frequency? 2 pi by n. I'll get only harmonics of this. Continuous time frequency, what does this map to? K 2 pi by n. In continuous time frequency, what does it map to?
Fs by n.
Kfs by n. Right? Where k goes from 0 to n minus 1. Okay. So now again multiplying these two guys, what will be the frequency components I'll get? Fn is multiplied with the sinusoid at kfs by n. What are the tones I'll get? Think of it as two sinusoids, right? Sine of this multiplying with the sine of this. What are the frequencies I'll get? I'll get the sum and difference, that's all, right? So I'll get kfs by n.
Plus minus F.
So for k equal to 0, I'll get basically plus or minus fn. That is the actual signal I want. So the images will be from 1 to n minus 1. So this will be for the images. Is that okay? So if I look at the spectrum, I'll have basically the actual sinusoid. In addition to this, I'll have a whole bunch of sinusoids. So one will be around fs by n minus fn. I'll have one at fs by n plus fn. I'll have two sinusoids around 2 fs by n, two more around 3 fs by n, and so on. Okay. So again, this is going to be a problem. So can you suggest a solution for this? Copy this. Yeah. So here we don't have an offset, we have a gain error. Erase all this. Okay. Yeah, okay. Yes. So here I'm having different gains, K1, K2 and so on. So what can be done to correct for this? Yeah, I'll have to somehow make sure gains in all the branches are equal. So what can be done for that? For the offset case, what did we do? We added or subtracted the error term here. So same thing can be done now. Right? So we can basically go and put a digital gain in each of these channels. And again, you can take one of these as a reference channel and try to change the scaling factor here using some kind of an optimizer, some kind of a algorithm here that will make sure that the gains in each of these branches is same. Again, here again we will resort to digital calibration. I mean, in some cases it turns out because of the way the ADC will be used at the system level, you might have an amplifier before this. This is because of the way the ADC has to be used at a system level. Okay, and this gain of this ADC is usually programmable. I mean, gain of this amplifier. So what you can do is, instead of correcting for this gain error here, you can also change the gain of this amplifier and correct it. Because in some applications you will find before the ADC you will need to have some kind of an amplifier to amplify the signal before digitizing. In that case, you can actually go and program the gain of this guy and do it. Either of them will do. Great. So what is the point of the filter? Tones you're saying. Yeah, the thing is it? Yeah. See, here I have considered only a tone at Fin. So in which case the image frequencies will be deterministic. So you are saying, why don't you put a filter and take this out, right? But you don't know what the input frequency is, right? See, here I have taken a simple sinusoid, but in practice I'll have a band limited signal like this. Then the image frequencies will be basically somewhere here and here shifted, right? So you can't do one filter. Okay, so let's look at the last non-ideality, which is, what is it? Yeah. So the last non-ideality is when there is an offset in the clock given to us. Right? So what will happen because of this? There is no gain error. So samples I'll get in the top branch is fine. Here in the bottom branch, what are the samples I'll get? Will I get x of ts? I'll have x of ts plus some delta t. Okay, let's say plus or minus, we don't worry so much, right? You'll also get some delta t and so on, right? So this is basically mismatch in the timing offset. So now if I take x of ts plus delta t, remember that delta t is compared to ts, do you think delta t will be smaller or larger? It's going to be much smaller, right? So how can I approximate this? Simple. That is very bad approximation. I mean, I have f of x plus delta x. What is the approximation, for that? I have some function. I know the value at x. What is the simplest approximation for the value at a small increment x plus delta x? Taylor series. Simplest thing is a linear approximation. You find the slope at this point. Do it, right? So it's x of ts, that value, plus the slope at that value point, times the, fine. So now this basically helps us simplify this thing. So now if I look at the samples I'll get, my x of n is going to be, first sample is fine, x of 0. Second sample is x of ts plus x dash of ts times delta t. Third sample is x of 2 ts. This will be x of 3 ts. So, right? So again, if I try to, to analyze it, the goal is the same. We try to represent this sequence in terms of the ideal sequence that we should have gotten. So this is the sequence. So how can I represent in terms of the ideal sequence? Yeah, but first term will 0. Second is basically x dash of ts times delta t. Third is 0. Fourth is, right? So it's not repeating, right? Remember. So this is the error sequence. So one way you can think of the error sequence is, see, we need to take the derivative of the signal at the sampling instance. So you can assume that we are taking the signal x of t. I'll take the derivative, and then I'll sample at ts. I'll scale by delta t. That gives me this. But remember that I'm not adding this error for all samples, only alternating. So what can I do to model that? I mean, remember, this is going to give me x dash of 0 times delta t also. I don't want that. No, but the thing is, our actual samples are at ts, so sampling rates must be consistent. This is sampled at ts finally, right? So to be consistent, everything must be at the same sampling rate. So what is the simplest thing I can do to model this? No, switches meaning, again, I can't change sampling rates. Okay, see here, what are the sequence I'll get? I'll get x dash of 0, x dash of ts and so on. I'll ignore the delta t. What should I get at the output? This should be 0. What is the simplest operation you can think of? That's all. Multiply by not zeros, right? What should it be? I should multiply this with what?
Another sequence of 0 and 1.
How should that sequence look like? Multiplying sequence?
0 and 1.
First sample should be 0, second should be 1, 0 and so on. Fine? So here it's going to be a sequence which is 0, 1, 0. Okay. So let's see how this error sequence is going to look like. So again, I'll assume the input is a sinusoidal Fn. After differentiation, the frequency is not going to change. Let's say after sampling, nothing happens. Scaling by delta t, nothing happens. So what is the frequency components of this guy?
0 and 1.
0 and pi. Again, it's a periodic sequence with two samples, only two frequency components. Again, I look at continuous time frequencies, it's 0 and fs by 2. I multiply these two, what are the images I'll get here? I'm multiplying a sinusoid at DC with a sinusoid at Fn. I'll get back my signal at Fn. That's okay for us. And the other thing I'll get is, and this is basically the image again. Right? So again, let's see if this what we get makes sense. So it looks like the error sequence we get is actually proportional to the slope of the signal at the sampling instant, right? Does it make sense? So this says that the error I can get if there is a mismatch in the timing offset, that is if there is an offset in the sampling instant, is proportional not to the signal, it is proportional to the derivative of the signal.
Yeah, so it will, if it's shifting, how much it will shift will be determined by the slope.
Yeah, so basically if let us say the slope is 0, signal is varying very slowly. So instead of sampling at Ts, even if I sample at Ts plus delta t, the error you make in the sampled level is negligible. But if the signal is varying very fast, even a very small change in the sampling instant will result in a large error. So the error will indeed be proportional to the slope of the signal at the sampling instant. Now, do you think this will be a problem for low frequency signals or high frequency signals? High frequencies. And notice that the whole point of having an interleaved structure is for us to able to digitize very high speed signals, right? So this will be one of the major non-idealities we have to tackle when you are having this kind of interleaved structure. Okay. Now, yeah, we saw that for a two-channel case, we get this image fs by 2 minus fn. If I extend it for n channels, what will be the images I'll get? I'll get k fs by n plus or minus fn. And k will be varying from 1 to n minus 1. Right? So again, let's see how we can tackle this timing offset. So I'll just copy this. Yeah, what can you suggest something to correct for this? Is there something that you can think of? See, one thing is, you can go and tackle the root cause of this issue itself. What is the root cause of this issue? The clock being not, and the time shift in the clock is not exactly what you want. So one thing you can have is generate clocks with multiple phases. There are circuits which can help us do that. And use the right phase for the clock that minimizes the image strength. Right? Other thing is you can basically try to take the clock and delay it by a programmable amount and then try to feed that as a sampling clock so that the error gets minimized. And what is the simplest way in which you can delay a clock?
Buffers.
You can put a buffer, but let's say I want to get a programmable delay. If I want to increase the delay in this, what can you do?
Increase the capacity.
So basically I can go and put a capacitor here. Let's say I try to change the capacitance. That way the delay you get will be programmable. That is one thing you can do. Of course, there are other things you can do. There are digital calibration techniques for this also. Basically, you try to estimate this guy and subtract it. The error you get is proportional to the slope of the signal. So there are algorithms that can help you detect the slope of the signal, and using that information you can digitally go and add some error sequence and correct for this. So here we have the ideal plus E of n. You can construct minus E of n, let us say, based on the slopes, and then you can do that is also possible. So bottom line, for both for both timing offset and for mismatches in the gain, the effect you see on the signal spectrum is same, right? Because you see these images at k times fs by n plus or minus fn, but for the timing offset, the error is basically dependent on the slopes. Okay. Actually, you can also understand this from a different angle. Maybe we can do that. Yeah. So let us say I have a 2x ADC, 2x interleaved ADC. This is the first ADC, second ADC. Each of them is operating at fs by 2, and the clock to the second ADC is shifted by ts. That's all taken care of. So the overall structure, it will be sampling at what speed? Fs. So if I put this in a black box, again, I'll also have a multiplexer here at the output. I'll also show that. So if I put it in a black box and give it to you, to the outside world it will look like it is an ADC sampling at fs, right? If this can sample at fs, what is the maximum signal bandwidth I can have? Fs by 2. Fine. Now if you see signal with a bandwidth of fs by 2, it's internally getting sampled by an ADC sampling at fs by 2. Will there be aliasing or no? Here there will be, but magically somehow if I look at the final spectrum, looks clean, right? So let's actually see that will also help us gain some understanding. So what I'll do is I'll try to model this mathematically. Again, we are only interested in the effects of sampling, not quantization, so I'll ignore quantization for now. So I'll try to model what's happening in the two branches. So in the top branch we are sampling the signal at fs by 2, right? How can I model sampling operation? How is sampling operation modeled mathematically? Multiplication with an impulse train, and this will be, let us say, delta of t minus, and what are the instants at which the impulses are there? No. Here sampling rate is fs by 2, right? What is the sampling period? 2 ts. So here what should I write?
2 ts.
Right? This is happening in the top branch. In the bottom branch, what's happening? This is also sampling at fs by 2, but what is the difference?
Ts.
There is a ts delay. So if I had to write this here, what should I write? T minus?
2n minus 1 ts. 2n plus 1 ts.
Fine. The same signal is being given to both of them, right? And the first branch will give these sampled impulses at 0, 2 ts and so on. The bottom one will give impulses at ts, 3 ts and so on. So to get the final data, I'll basically sum up the two. Mathematically, that's how we can model this. Fine. So I basically sum up the two. Okay. I'll remove this. So let's actually look at the frequency spectrum. So again, this effective thing can sample at a sampling rate of fs. So the signal can have a maximum signal bandwidth of fs by 2, right? So let us say this is the signal. It is spanning from minus fs by 2 to plus fs by 2. So here we have this impulse train. If I look at the spectrum of this impulse train, how will it look like? It will again be an impulse train, and where will the impulses be located? Where will be next thing? Huh? Yeah, 1 by 2 ts, it's fs by 2. Next thing will be at fs, 3 fs by 2 and so on. So if I multiply these two guys, what will happen to the spectrum here? In time domain it's getting multiplied. Convolution. So this guy will get repeated around each of these frequencies. Right? We again saw this in the first class. We'll have replicas of the sampling, of the input spectrum. I'll have one replica around DC. Where will be the next image or the next replica be located at? Around fs by 2. So it will be centered around this point. So we'll have something like this. We'll have severe aliasing. This will be fs. So we'll have the next thing here. Fine. Okay. Now let's see what happens in the bottom branch. So in the bottom branch, again I have a train of impulses. If I look at the spectrum, what will it look like? Periodic train of impulses. The thing is, let us say this I call it as some p delta of t. How can I write this in terms of p delta of t? So if this is some p delta of f, what will be the frequency, the Fourier transform of this guy? P delta of f? Huh? Okay. So it's again going to be a train of impulses with an additional phase shift, right? So here again I'll have the same impulses, 0, fs by 2, fs and so on. What will be the phase shift at f equal to 0 here? Nothing. So let us say I normalize everything to 1. Here also it will be plus 1.
I don't know why, but why fs by 2 fs by 2?
This is a train at
2ts, right?
Yeah, 2 ts, 1 by 2 ts, right? It's a impulse train periodic at 2 ts. 1 by 2 ts fs by 2. So what about the frequency shift? What about the phase shift at fs by 2? If I put f to be fs by 2, what is the phase I get? Pi. So e power I have j pi. So what is the scaling factor? Minus 1. What can you say about the next one? Plus 1. It will be alternating 1 and minus 1. So if I actually look at the spectrum for the bottom, how will it look like? Yeah, so essentially for even frequencies around multiples of fs, the images will be fine. But around multiples of odd multiples of fs by 2, the spectrum will basically flip like this. Right? Sorry, here. Something like this. How should it look like? Yeah, sorry, something like this. Messed up. Where will it look? So here, whatever, right? You understand. So now if I add these, what will happen? Basically, I'm adding these two. What will happen now? So these guys will get cancelled with these guys. So only thing that will remain is so note that in this case, each individual ADC has terrible aliasing, but when you add these multiple parts, those image frequencies will get cancelled, right? And in particular, if let us say the input is a sinusoid at Fn, the image will be located at what frequencies? Yeah, remember that this frequency will get shifted around each of these frequencies. So we'll get one at Fn, that is the desired frequency. We'll also get at fs by 2 minus Fn, and so on. So here also the image will be at fs by 2 minus Fn. But what you will find is that the image in the two channels will be of the same magnitude but with opposite signs, and so they will cancel. And the key to this cancellation is the magnitude of this is exactly 1. And what about the phase shift? Phase shift is what, in angle, what is the phase?
180.
It's phase shift of pi. So this has a phase shift of pi, and that is why when you add the two, it exactly cancels. But if there is any mismatch in the gain, this will not get cancelled. You will end up with this image frequency. That is what we also saw. If you have any kind of gain errors or gain mismatches, the image frequency will be there. Similarly, even if you have any error in this phase, see here the phase is pi, because its delay is Ts exactly. So if there is any error in this timing offset, then the phase will not be exactly 180 degree, and again the cancellation will not happen. So again, even if you have a timing offset, these images will not get exactly cancelled, and you will still have a small residual image. Is that clear? Great. Okay, this should not, I think I messed up here. This is what I messed up. So this is the image. Okay. And again, this is for a 2-channel case. For an n-channel, the images will be located at what frequencies? Yeah. So let us say for a 2-channel case, I just have one image to worry about within fs by 2. For n channels, how many images I should be worried about? N minus 1, right? Because remember that in n-channel case, each ADC will be sampling at what frequency if the total rate is fs by n. So we'll have images around multiples of fs by n. So we'll have around DC, that is the main spectrum, no issues. Around fs by n, around 2fs by n, and so on. So we'll have a total of n minus 1 images within 0 to fs by 2, right? And here you see that in the 2-channel case, the phase shift of these images between adjacent samples, adjacent channels is pi. Similarly, for an n-channel case, the phase shift of the images between adjacent channels, what will that be?
Pi by n.
No, for 2 channels it was pi.
Pi, oh, 2 pi by n.
It will be 2 pi by n. Okay. So basically now what you will have is, you will have n images, magnitudes will be same, relative phase shifts will be 2 pi by n. Again, if you add 1 plus, if you add sinusoids at e power j0, e power j 2 pi by n, and so on till e power j, right? What is this? You add sinusoids with equal phase shifts throughout this 2 pi to 0. And that's why even in the n-channel case, if the gain and the timing offset is exact, then all the aliases will cancel and the images will not be there. But if there is any kind of mismatches in the gain or the timing offset, you will end up with a severe disk. So the bottom line, when you do this time interleaving, you can have 3 different issues. One is the mismatches in the offsets of the ADCs, and if you have mismatches in the offsets, what will be the additional frequency components that we will see? So we'll basically get the tones at kfs by n, because offset was simply adding an error sequence like this. So it was a periodic sequence with a period of n samples. So the additional tones we'll get is just this. But if you have mismatches in the gain or in the timing offsets, what will be the additional frequency components we'll see? You just saw, right? If input is Fin, what will be the frequency components extra that will be present?
Fs by 2 plus fs by 2 minus
For n channel case, what is it?
fs by 2 k.
So we'll have this image frequencies present. And as I mentioned, this time interleaving is the way in which all high-speed ADCs are designed, especially in serial links. And it is not uncommon to have number of channels to be 64 or so. And again, see, in all these serial links where we have this wired communication, these ADCs are really required, because if you think about it, in in this wire transfer through USB or LAN, you are interested in transferring ones or zeros basically, right? So ideally you want to transmit for 0 something like this, 1 something like this, and so on, right? Let's say 0 1 0 something. But from the transmitter to the receiver you have a short wire. That wire ideally is not a short circuit. It will have a distributed R's and C's. So because of that you will end up with a distorted waveform like this. So at the receiver end you have to make sure whether the received signal is greater than some threshold or less than some threshold. So you need to have an ADC. Okay. And in principle you can have a single bit ADC to see if it's greater than something or less than something. But in practice due to other constraints you need little bit more resolution. And also what is done now is, see, instead of just sending data like this, what we do is we group the information in groups of 2. Let us say the pair is 0 0, you transmit one amplitude level. If the data pair is 0 1, you transmit one more amplitude. 1 0, it's another amplitude. So between 0 to VDD you can basically have 4 amplitude levels, and now you see that in the same time interval I am transmitting information about twice the number of bits. So this way your throughput will be easily doubled. Have you seen this somewhere? Have you taken any modulation courses, communication courses? Okay, this is called PAM4, pulse amplitude modulation, with 4 levels. Okay, and in this case, as you can see, at the receiver, the received signal will be terribly bad. So you need to make sure whether the received signal is greater than each of these levels. So you need more resolution, and in practice you need around 6 bits or so to actually decode this properly. And the speeds can go as high as hundreds of gigabits per second. Okay. So let me just show some couple of things. So again, this is a recent paper in Journal of Solid State Circuits, very recent, and this paper is from actually Intel. So everyone is from Intel. It's basically from Intel. Okay. And Intel is one of those leading companies which has been pioneering and designing high-speed serial links. So here basically this paper is not just on ADC; it's an entire receiver in this serial link, and you can see it's a ADC based receiver because you need the ADC is the final block that makes a decision on whether the transmitted bit is 0 or 1, whatever, right? And you can see the speed, right? 224 gigabits per second. And they have done this by having a 64-way time-interleaved ADC. Okay. And they have this PAM4. See the thing. So this is the interleaved ADC, and again this time interleaving is a general principle. It is not necessary that you have to interleave only flash ADC. Any ADC you can basically go and interleave, right? And in practice, I mean in the recent times, instead of interleaving flash ADC, since we need around 5 to 6 bits of resolution in these interleaved applications, instead of going for a flash, people use SAR ADC, which we'll see later in the course, and they do this. So here I'll show one other thing. So this again a recent paper in JSSC in 2023 April, and this is also from Intel. I think it's also from Intel. So here this is essentially an ADC paper where they have realized 4x interleaved ADC at this speed, right? And the deal here is, oops, what are they? Sorry. If you recollect, in the last class I mentioned that so the current trend is to try to push more and more processing in the time domain. So what they do is you have convert the voltage to time and then do digitization in time, and then they have interleaved four such structures to get this. So let's actually look at the final output spectrum and do some calculations. Yeah. Let's look at this output spectrum and make sense of this. So here, this is 1.9 gigahertz. So it means what is the sampling rate? 3.8. This is fs by 2. So my fs is going to be 3.8 gigahertz. The input frequency is 0.2 gigahertz. So if there is any mismatch in the offsets in these 4 channels, remember the number of channels interleaved is 4. If there is any mismatch in the offsets in these 4 channels, what will be the additional frequency components I will see?
Yeah.
Kfs by n. So k times fs is 3.8 gigahertz by 4. This is 0.95, right? So I should see one tone at 0.95 for sure. Now if there is any gain error, that is mismatches in the gains of the 4 channels, what will be the frequency tones I'll see? Kfs by n plus or minus Fn, right? So Kfs by n is k times 0.95 plus or minus 0.2. At least for k equal to 1, what should be the frequencies I should see? 0.75 and 1.15. Right? So now you can see this is the offset mismatch. We expect, yeah, around 0.95 is what you get in offset, and you can see the gain mismatch is the green ones. So the green ones you see one at 0.75. Sorry. So this is the guy. You see one at 0.75 and one more at around 1.15. So let's look at the last one also. That might require some more calculations. So here again we'll do the same thing. This is 1.9. Fs is 3.8 gigahertz, and input is 1.6 gigahertz. So first tell me where will be the second harmonic here? Where will the second harmonic be located? 3.2, but remember we are plotting from 0 to fs by 2. Where will this alias back to? Second harmonic ideally should be at 3.2. Where will this alias back to? 3.8 minus 3.2, which is 0.6. Similarly, third harmonic, where will it be? Third harmonic will be 3 times 1.6, which is 4.8. Where will 4.8 gigahertz alias back to? Around 1 gigahertz, right? So again, if there is any gain error or mismatches in the gain in the 4 channels, I'll get Kfs by n plus or minus Fn, right? So this is k times 0.95 plus or minus 1.6. For k equal to 1, what are the frequencies I should get? 0.95 plus 1.6, what is that? 2.55. And other one is, I think, 0.55, right? 65, yeah, sorry. 0.65 will be present here. 2.55 it will alias back, and it will alias back to what frequency? 3.8 minus 2.55, which is what? Around 1.25. Okay. So again, I'll remove this and show the results. So let's look at everything. Second harmonic was supposed to be at 0.6. This is HD2, the second harmonic, somewhere around 0.6. Third harmonic is around 1. So this is the third harmonic, around 1. And due to gain error or mismatches in the gain, we expect 1 at 0.65. So gain mismatch tone is the green one. This is around 0.65. And the second tone is supposed to be at 1.25, roughly around 1.25. So again, the point of this exercise is that you should be very fluent in knowing where each aliasing tone is coming. Okay, because the moment you have interleaving, along with harmonics, we are going to have a whole bunch of other spurious and imaged frequencies. Should be very fluent in knowing where, if you take an FFT, where each tone will come. Okay, cool. So you can stop here. Yeah.